Experiment is any observation of a random phenomenon. So you guys kind of know an experiment. If I say, what's probability of flipping a coin versus actually picking the coin up and flipping it? Outcomes are the different results of the experiment, and a sample space is the set of the outcomes. So they're very similar, kind of the same thing. An event is what you do, like the event of flipping a coin. So flipping a coin, landing on heads 3 times would be an event. And then odds are very similar to probability. They are the likelihood of something occurring versus the event not occurring. And a complement is 2 probabilities from the same set that have a sum of 1. So again, this is just a general vocabulary list. So let's talk about our first term that we have to know. So on a test or homework, it'll say, what is the sample space? So this one, if they say that we select an iPad from a production line and determine whether it is defective, we have a sample space. Like, what could possibly happen if we pick an iPod from a production line and we're going to test if it's defective? Well, the only 2 options, when we do sample space, we put this bracket-like thing. Is there anybody who can't see what I'm doing or hear me? All right. So one thing is I'm going to try to do cursive with this thing. The iPad could be defective, or it could be not defective. And that, oops, is what we call the sample space. Like, what could possibly happen? The thing could be defective or not defective. That's called the sample space. These 2 things are the outcomes. Okay, so that's just vocabulary. More on sample space. We have 3 children are born to a family, and we note the birth order with respect to gender. Assume that only 1 child is born at a time, meaning there's no twins or triplets or anything like that. So this right here is a little tree diagram, kind of like our heads and tails things, but it's a boy and a girl. So it's very similar to the coins. Our sample space would be writing all of the outcomes all together in a bracket form. Well, one outcome is boy, boy, boy. So we would write boy, BBB is fine. And then you could get a boy, and a girl. And this means if you have 3 kids, your first one might be a boy, second one might be a boy, third one could be a boy. What are the different outcomes? Okay, then we could have boy first, then a girl, then a boy, and you can go through this tree diagram and pull up the sample space. Then it would be girl, boy, boy, girl, boy, girl, and girl, girl, boy, and then all girls. So this whole thing is the sample space, and each one of these inside is an outcome. So that's really the difference. They're almost like the same thing. A bunch of outcomes makes the sample space. Okay, so we kind of did that. We just didn't call it those particular things. And then we have this sample space. It says we select 1 card from a standard 52 card deck. Without returning the card to the deck, we select a second card. We will assume the order in which we select the cards is important. So when we do this sample space, you can actually list the outcomes. For example, you can get an ace of hearts, or an ace of diamonds, right? You can get an ace of hearts and the 2 of diamonds. And you can keep going, and then you could get the 2 of hearts and the ace of diamonds, and it goes on and on forever. So this sample space is way too big to list. So what we would do is we would go back to our counting principle and just say, how many outcomes? So we did this last chapter to figure out how many different ways we could pull two cards and what they could show, like a king and a seven, different suits. So what we would do is the counting principle. So we're going to pick two cards. The first card, if we just put this 52 card deck, face down, pick a card, how many options of cards do we have? We have 52 cards that we could choose from. Then, without returning the card to the deck, we pick a second one. So we pick a card first, we don't put it back. That leaves us with 51 options for the next one. And then what do we do when we do the counting principle? Is we multiply them. So we could sit there and list all these, or we can just, if it's too big, we're just going to say how many outcomes are in our sample space. And that is actually 2,652 different outcomes. So if it's too big and it's asking for your sample space, you're just going to say how many outcomes there is. Okay, because we can list this, but then we'd have to do it properly and list 2,652. Well, that's ridiculous. This one here, sample space, we rolled 2 dice and observed the pair of numbers showing on the top faces. Again, you can list them, but this right here is the sample space of rolling 2 dice. These are the outcomes. All of these in here is there's 36 outcomes in the sample space. So is everybody clear on what the difference between the sample space and the outcome is? Sure. All right, so let's move on to probability. So if you've ever worked with probability before, probability falls between 0 and 1. You will not have a 250% chance of doing something. It's either 0, any number in between, 1, okay? Then 0 probability is impossible. And if you have a 1 probability, then that will definitely happen. They sometimes turn these into percents. So this would be 100% probability, right? This would be 50%. Sometimes our probability is in fractions. So this would be 1/2, right? This would be, I don't know, 5 out of 5, 6 out of 6, whatever. And then you have all of our answers for probability are going to fall within 0 and 1. So if you're getting answers of probability that are like 2.5, that can't be correct, okay? So that's how probability works. It's going to fall into numbers in between 0 and 1. All right. Now we have this formula right here. It is the probability formula. How do you find probability? So if you ever did simple probability, it's this formula. This is very wordy, but it's technically the formula, but it's actually very easy. So it says P for probability of E. E is what we call an event. So if I say, what's the probability it's going to rain? Then rain is the event. Okay. And then the number of times E occurs. So in our problem, that's the number of times it could occur. So we would look at our outcomes and count up how many there are. And the number of times the experiment is performed. It could be an experiment or just the total number of outcomes. Okay, so it's whatever they're asking us to find the probability of over the total. That's how you find probability. All right, so let's do the probability with this chart. Everybody with me? Sleeping? All right. So it finds 2 probabilities based on this chart. So it gives us this big old wordy thing. A pharmaceutical company is testing a new flu vaccine. The experiment is to inject the patient with the vaccine and observe the occurrence of side effects. So assume that we perform this experiment 100 times and obtain the information in table 13.1. So even if you weren't given this information, let's say it doesn't tell us how many times it was observed, all we would have to do is take this right here and add them together. So sometimes it might just tell us, other times we're going to have to look at the total and we're going to have to add it together to get the total. Okay, so first question, what's the probability that a patient will have no side effects? So no side effects is our event. So the probability of no side effects is how many no side effects do we have? We look down at our chart, we have 72. How many do we have total? 100. I mean, turn that if you want into a decimal or a percent. 72%, 0.72, or 72 over 100. Pretty easy. What's the probability that a patient will develop severe side effects? So severe side effects time is our event. So we're going to do the same thing, but this time it's the probability of severe side effects. So we're going to do the severe number up here. So we look down on our chart, we have a 3. And we're going to still do the total down here, and that's 100. And 3 out of 100 is 0.03, or 3% if you turn them into percents. And probability turned into percents will not go more than 100%, because decimals to percents, we should know. So simple probability is basically pretty simple. It is what they're asking you to find over the total outcomes, and your outcomes should be listed somewhere in your problem. Or you can figure it out by knowing how many cards in a deck or whatever. All right. Any questions so far? Because now it gets a little more difficult because we do things like permutations and combinations. So we have to do counting formulas, okay? Counting formulas are our P for permutations. Oh my gosh. Sorry. There's a spider. So counting formulas are permutations and combinations.
Burn it.
Burn it. Ugh.
It must die.
Agree.
If it comes back, I might have to take a little 30-second break. All right.
I'm sorry. The whole school's got to go now. You just got to burn down the whole school. Like, I'm sorry. Like that's not acceptable.
A spider? It's better than a mouse. Maybe. I
No.
guess what kind of spider? I don't know. They're doing these things called fogging the classroom. I don't know if that's like some new method of cleaning them, but I just got an email today that they said they're fogging them. I don't know what that means.
It's essentially a toxin that's released into the air that kills pretty much all creatures. Like if a human were to breathe it in for a prolonged period of time, like they too would die. But it's significantly more impactful on insects and other creepy crawlies.
Oh, well, maybe they haven't gotten to my classroom yet. So, I don't know if fogging is for bugs and mice or if it's for germs, but whatever. All right, so let's go back to this. We're going to do simple probability with counting formulas. So these two are probably the most difficult probabilities you'll have to do because you have to do permutations and combinations within the probability. All right, so it says we draw a 5-card hand randomly from a 52-card deck, okay? So basically, if we do this, my computer now died. Are y'all there? Can you hear me? Okay, all right. I don't know what happened. Okay, so if we just do drawing a 5-card hand randomly from a standard 52-card deck, that means we would go back to our counting principle, right? And we would say we're going to pick 5 cards, right? And we're just randomly picking them. And we're not going to put them back because we want 5 cards in our hands. We're not going to pick one, put it back. That would leave no cards in our hand. We want 5 cards in our hand. So if we just put a deck of cards down on the table and picked 1 card, we would first have 52 options of different cards. Then we would have 51, right? And then we would have 50, and then 49, and then 48. Okay, and then we would multiply all that together. And when we do that, that's called a combination. Okay, because it's random, there's no particular order. So another thing we could do is combination 52, 5. This is going to give us the total number of different cards we can end up in our hands if we pick 5. Okay, so if we do combination 52, 5, there are 598,960 total different 5-card hands that you can have. Maybe you have an ace, 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 and a king of all the different suits, right? And so all these suits matter too. So this is the total different options we can have. Okay, so when we do our probability, the total is going to go on the bottom of our fraction. And then it says, what is the probability that we draw one particular hand? So we're just going to do 1 up here. So the probability is 1 out of 2,598,960. If I said to you, okay, I want you to pick the ace of hearts, the king of diamonds, the 3 of spades, the 4 of clubs, and the 2 of hearts. You'll get that one time out of 2,598,960 chances. Okay, so that's the probability. When we do this one, if we draw a 5-card hand from a standard 52 deck, again, we're doing the same thing up here. So our total is going to be the 2,598,960. Okay, that was our combination 52, 5. That was our total. Then it says, what's the probability that 5 cards are hearts? So when we do this one, we have to think of, okay, so how many cards in a deck are hearts? Does anybody know how many hearts are in a deck? It goes ace to king. How many is that?
Well, if you divide 54 by 4, then you have the answer. I don't know how to do math, so.
Isn't it
You mean-
13? All right, 14.
It's 52. 52, right? And there's 4. You guys don't know? How many, you guys play cards like all the time, maybe. I don't know. There's not 14.
13.
No, he's right. It's 13.
13.
There's 13. 13 of all the things, right? So we are still picking, we're not going to put a 13 here because it's asking us for the probability that we get 5 cards again. So for this one, we're going to do combination 13, 5. That's going to represent how many different ways we can get 5 hearts in our hand. Maybe it's the 2, the 3, the 4, the 5, and the 6. Maybe it's the 3, the king, the queen, the 6, and the 8. So we'd have to do 13, 5 for our combinations. And that is 1,287. Okay. So I will tell you, most of your probability is like this simple probability. What they're asking us, the event, over the total. This is still what they're asking us that we're going to pick over the total, but it was a little more complicated to get that total. And if we're picking more than one card, we'd have to do a combination. Okay. So does everybody understand why we did combinations for these? Reason was we were picking 5 cards at a time, or 5 cards total, instead of just one like up here. All right. So let's talk about odds. Odds are very similar to probability, but we don't put them over the total. Okay. When we write odds, we are either doing odds against something or in favor or for something. Okay. So it's against and for. When we write these odds, we would write them as N is standing for the odds. I don't know why they pick N, but they just do. Okay. In this one, this is against. And for, or in favor of. And you could switch it around because you might be asked for the odds for something. Okay. These two things are called complements because they equal the total number. They equal the total. So they're like probability, but not necessarily the same. So we can think of this as a very simple problem. If I tell you to compare it with probability, let's say the probability of picking a red marble in a bag is 3 out of 10. Let's say that's the probability. I can very easily just take this information and turn it into odds. Okay? This means that if I have a probability of red being 3 out of 10, do you agree that the 3 would represent there are 3 red marbles and there's 10 total marbles? Okay, that's what the probability is representing. So now I know there's 3 red marbles in the bag and 10 total. So if we're doing odds, we're going to say, what would be the odds, let's say, for picking reds? They're a little different because we don't do the total down here. Okay, probability, you do the total. If I'm doing odds for red, I'm going to do red to not red or everything else. Does that make sense? So odds are going to be 3 red. How many not red? Well, if there was 10 total, 3 of them were red. Do you agree that 7 would have been not red? It's pretty, just kind of think of it a little bit different. When we write our odds answers, we put this little colon here, 3 to 7. That's how it's read. That's what this represents. Okay, so I know this is a lot of words and it looks like complex, but it's actually pretty simple. But what if we did the odds against red? Against red would just be this flipped around. Because if we're doing against red, we're going to do not red, because that would be against red, over red. So that would be 7 to 3. You understand that idea? Anybody have questions on that?
I mean, a little.
A little what? A little question?
Like, I understand it a little bit, but it's just like,
Just like what?
just kind of confusing still for some reason.
What would be the probability? Let's say we pick a 4. Maybe I shouldn't use numbers because that'll be confusing. They'll be like, what's the 4 represent? All right, let's go probability of blue. If the probability of blue, let's say we have a bag of marbles, there's 10 blue and, I don't know, 17 marbles in the bag. So if the probability of blue is 10 to 17, that means there's 10 blue, according to our probability formula, and 17 total. Okay, if we turn that into odds, let's say I'm going to say odds for getting a blue would be blue over not blue or everything else. So if I know the probability of getting blue in this bag of marbles is 10 over 17, my odds for getting blue would be 10 still, because I have 10 blue, but not 17 here, because 17 is the total number of marbles. 10 of them are blue. How many are not blue? 7 of them. Okay, so 10 to 7 would be the odds for blue. And then against blue would be 7 over 10. Okay, so maybe we'll practice some more here.
Okay, I understand that a little bit better now.
So here I put the sample space for our dice. So this is saying we rolled 2 fair dice. So that's just saying, okay, we're rolling dice, 2 of them. These are the possible things we could get. So I put the sample space already in here for you. That's what this picture is for. We're just going to use this to help us answer these questions. That are not a 9 over those that are 9. Okay, so if you're doing against, you're going to do not 9 over the ones that are 9. So we go to our little sample space and we look at the outcomes. How many are 9s? Well, here's my 9s, 6 and 3, 5 and 4, 4 and 5, and 6 and 3. All of these, yes? These will make 9. There are 4 of them. 4 of them are 9. A sum of 9, yes? So then we would have to know how many are in this sample space. You could count up all the other ones that we didn't circle or cross out or whatever. Or you can just say, all right, well, this sample space has 6 outcomes this way. There's 6 outcomes this way, and 6 rows of 6 is 36. Okay, we're not going to put a 36 here because 36 would have to do with a probability. That's the total. Odds is not the total. Okay, you don't put that in your odds setup. So if 4 of them are 9s and there's 36 total, that must mean that 32 of them are not 9s. So you can go through and count if you want, or just use basic subtraction and say there's 36 in all. 4 of these have to be 9s, 32 are not 9s. So your odds would be 32 to 4, but the better answer, or the one that's more correct, is 8 to 1. Where does the 8 to 1 come from? Anybody have any idea? Please?
You just divided, didn't you?
Yes, I just basically simplified this because I could divide both of these by 4. So I basically just simplified this fraction. Okay. All right, so let's do the next one. See what we got. We are next going to do odds against a total of 3. So if we're going against a total of 3, we are doing not a 3, because that would be against 3s, over all the ones that are 3. So you go through your chart and you find where the sum of 3 is, and that's these 2. So there's only 2 of them that equal a 3. See, there's only 2 that equal a 3. How many others don't equal 3? Well, you can count them if you want, or you can do basic arithmetic and say if there's 36 total and 2 of them are 3s, then that must mean there's 34 left over. 34 of these are not 3, and 2 of them are 3. Then we can actually take out a 2 out of both of these, like you're simplifying a fraction, right? Oops, that's not a 2, that's supposed to be a 1. Duh. And we would write our odds 17 to 1. Better? No? I don't know. All right, let's try some more. Odds aren't that difficult. It's very similar to probability, but it's not this over the total. It's this over everything else. All right. What are the odds for a total of 6? This time we want the 6. Okay. When we do 4, 6, we want to do how many add up to 6 over how many that do not add up to 6. So you go back through your chart. You go, how many equals 6? Well, here's my 5 and a 1 and a 4 and a 2 and a 3 and a 3 and a 2 and a 4 and a 1 and a 5, right? All of these add up to 6. There is 5 of them that add up to 6. If there was 36 total, that must mean 31 did not add up to 6. This cannot simplify, and you would just write your odds 5 to 31. And then the last one, what are the odds for a total of 3? So for a total of 3, we want to do, since it says 4, we want to do the 3's over the not 3's. You can go back to your chart or just remember that, oh, up here we did not 3 over 3. So all I have to do is flip those around. 2 of them were 3. 34 of them were not 3's. 2 over 34 simplifies to 1 over 17. And so when we write the odds, we're going to write 1 to 17. Now, what do you notice about your odds? Hopefully you notice. This total 36 was the total outcomes in my sample space, right? When you do odds, these two numbers here, when I add them together, like top and bottom, they will equal the total number. So the 36 is not part of this. We're not putting everything over the total. That's probability. But when you do odds, make sure that these two add up to the total number of outcomes. Questions on those? All right. So let's use probability and odds and figure out how we're going to answer certain questions. Not too difficult. So here it says we're flipping 4 coins. I did a little sample space for you. I did the tree diagram. And so here are the outcomes. So we're focusing on this. So we have 1 flip, 2 flip, 3 flips, 4 flips. This is what we would get instead of us having to do the whole tree diagram. Here it is. So let's see if we can answer these questions. How many elements are in the sample space? How many elements or outcomes are in the sample space? What would you do? You go over here and you count them. If you remember when we did flips before, there was 2 options on the first flip, and then there was 4, and then there was 8, and now this one's going to be 16. So you can count down through those, or remember if I'm flipping it 4 times, there's going to be 16. Now we've got probability. What's the probability that there are more heads than tails? This is our event. So remember, when we do probability, we do probability of whatever event they're asking us is how many of that event over the total. And I have to go back to, we're doing probability, not odds. So now we have to go through our answers here and say how many, count up, how many have more heads than tails? Well, that means 3 heads and 1 tail. Let's see. At least 3 heads and 1 tail. So we got 1, 2, 3, 4, 5. 5 of them, right? Everything else doesn't work. So there's 5 outcomes that have more heads than tails. How many outcomes were there? 16. So 5/16 is your probability. C says what's probability that there are an equal number of heads and tails. This is our event. When we do the probability of equal number of heads and tails, we're going to do the number of heads and tails, equal number of heads and tails over the total. How many have an equal number of heads and tails? That means 2 heads and 2 tails, right? That's an equal number of heads and tails. So we have this one, this one, this one, this one, this one, and this one. So all my light blue ones I kind of marked, right? 2 heads, 2 tails, 2 heads, 2 tails. Did I miss any? That's 6 of them. And then we would always take our probability and simplify it. I know I can take a 2 out of those. So I'm going to make it 3/8 probability because I just divide it by 2, like simplifying a fraction. So probability isn't that bad. Okay, it's kind of simple. Everybody good with that? All right, so let's the thing with the cards. All right, so this all right up here just talks about what is in a deck of cards so that we know. Okay, so we all know it has 4 suits. That would be the queens, are the hearts, the aces, the clubs, and the diamonds. 13 cards in the suit, and face cards are jack, queen, and king. Find the probability of the given event, and then find the odds against the given event. So we're doing the probability and odds against. So let's look at A. We draw a heart when we select one card randomly from a standard deck. So we're going to pick a card. What's the probability? We're going to get a heart. When we do probability, it's going to be the heart, because I'm asking, over the total. Well, how many hearts are there? 13. How many cards in all? 52. And then we would simplify that. And that would be 1/4. Because you can actually divide by 13 out of both of those. So this is just simplified. So we have a 1 in 4 chance of picking a heart for probability. Okay. Odds against. So we want to do the odds against a heart, which means we're doing the odds of not a heart. So when we do odds, we're doing not the heart because it's against. If it said 4 hearts, we would put the hearts first. Not heart over heart. I already said over here that there's 13 hearts and there's 52 cards in all. We're not going to put a 52 here because there's not 52 not hearts. If we're saying 13 are hearts, how many are not hearts? You would have to do simple algebra or simple operation of subtraction. 52 minus 13 is 39. So 39 not hearts, 13 are hearts. We can simplify that because we can take a 13 out of each, and it's 3/1. But then when we write odds, we'll write it like that, 3-1. There's a 3-1 chance to not get a heart for the odds. Next one is we draw a face card when we select one card at random. So this time we're doing the face card. Remember, these are the face cards. 3 face cards and 4 suits. So there's 4 jacks and 4 queens and 4 kings. All right, so probability of a face card would be a face card over the total. How many face cards are there? I told you there's going to be 4 jacks because we got hearts and clubs and aces and spades. There's 4 of these and 4 of these and 4 of these. So there's 12 total face cards in a deck. And then for probability, you put it over the total, and we already know that. Here we go. 52 is our total. And then, of course, we're going to simplify that. I think you take out a 4 out of both of those. That would make 3 and 13. So 3 out of 13. So when you do your probability, they're just fractions, but then just simplify them. Now we're going to do the odds. But then again, remember up here it said find the odds against this given event. So if this was drawing a face card, we want to do the odds of not getting a face card. So we're going to do not a face card. Oh gosh. Over a face card. That says face, believe it or not. I'm sorry. All right. So we can go back to our probability information and say, okay, well, we figured out there's 12 face cards. So that can go down here. We know there's 12 of them. And there's 52 cards total. So how many would not be face cards? 52 minus 12 is 40. And then we can simplify that because you can take out a 4, and that's 10. That's 3. So our odds would be 10 to 3. So you understand the difference between probability and odds? Anybody have a question? Is anybody still there? Oh, some people left. If you guys putting things in chats, I can't see. Oh, one person's answering me. Do you not have a speaker, Alexander? I don't know.
No, I just didn't want to interrupt you. I was the one
What?
that was talking about you have to burn the school down.
You can talk as long as we're talking now, right? Oops. Okay, so we're good with that? No questions. All right, so let's see what we got next. We're almost done, I promise. I think it's just this page and this page, then we're done. Let's see if we can do these. It says, in horse racing, a trifecta is a race in which you must pick the first, second, and third place winners in their proper order to win a payoff. If 8 horses are racing and you randomly select 3 as your bet in the trifecta, what's the probability that you win? Well, first of all, we must understand we are placing one bet, but that one bet, we have to choose 3 out of 8 horses in the correct order. So trifecta is much different. I don't know if you ever went to the horse races. They're kind of cool, the PV ones. But anyway, you can go and you can say, oh, I'm gonna pick Charlie horse, get it? And I'm gonna pick Charlie as my first one. And you sometimes just pick who's gonna win. But in this thing, you have to pick who is gonna not only win, but which horse is gonna come in second and which horse is gonna come in third place. So you got to kind of understand what the question is saying to you to begin with. And that's what it's saying. So we're going to have to do the probability that we're going to win. Okay. Or that we pick the winner. 3 winners. Okay. So we get one bet. That's it. We get one pick. We got to choose 3 horses, once. Okay, so I have to name who's first, second, and third just in one bet. So our bet is only one. But then when we do down here choices, here's where we have to pull in permutations and combinations. We are picking 3 out of 8 and the order matters. So what are we going to do down here to figure out how many ways you can pick 3 horses out of these 8 in a first, second, or third place? What do we do down here? Think of last chapter. If order is important, it's going to be a what? Did anybody say it?
Permutation or something like that.
The permutation.
Yeah.
So the bottom is going to be, thank you, permutation 8-3. And then we have to mathematically calculate that. You can put that in your calculator. If you remember how to do it, or use your Desmos. If you're doing a TI-84, you hit 8, the math button, and then go over to PRB, and then hit your permutation. And that is, you have one chance, one bet, and there's 336 different ways that these 8 horses can come in first, second, and third place. So you have a 1 out of 336 chance to win. Which isn't as bad. Lottery's harder, isn't it?
I really hate to be that one dude, but what the heck is a permutation?
The permutation is an order of ways you can, it's like an ordering, like how many ways can you pick these eight horses in first, second, and third place? So maybe we have a horse named Tom and Bob and I don't know, Joe. Those are our horses. Okay. Do we pick Tom, Bob, and Joe? But there's 8 horses. And then there's Charlie horse and there's Sally or whatever. There's 8 horses. So a permutation is an order of how you can put a certain number of total things into a particular order. And then the last one is odds. So this one says, suppose the probability that the Yankees will win the World Series is 0.3. What I would do first is I would take this 0.3 and turn it into a fraction. 0.3 is 3 out of 10. So when this is probability, the 10 is our total when we're doing probability, right? And the 3 is the event, and our event is winning. So right now, just by knowing that the probability is 0.3, we know that 0.3 is also 3/10. 10 is our total, and 3 is going to represent our wins when we go down here and do the odds. Does that make sense, everybody? Turn your decimals into fractions, and then you have your 2 numbers, and you could figure out whatever they're saying here over the total. So A says, what are the odds in favor of the Yankees winning? So if we're doing the odds for this, we are doing in favor of winning over not winning. That's what this is asking us to do. The odds in favor of winning. So it would be winning over not winning. So go up to here. And 3 was the number for winning. And if 10 was the total, what's going to be the number for not winning? So 10 was the total. So there's 7 not wins. So for odds, it's 3-7. And then here are odds against the Yankees winning. So when we do this odds, it's against winning. So it's going to be not winning over winning. Basically, it's this answer right here, just flipped, reciprocated. 7 not wins, 3 wins, 7-3 odds. Questions on any of those? No? So it's basically probability. Okay, some of the probability has permutations and combinations in it. Remember, permutation is an ordering of things in a certain order. Okay, when we went back here, we used combinations. Where was it? Combinations up here, because it didn't matter the order. We didn't have to have an ace first and then a king and then a queen and then a jack. The order did not matter, so we did combinations for that one. So just remember that when you guys are working through the probability with them. Okay.